Elon Musk was wrong. The man who made reusable rockets reality said one thing couldn't be done, and Sierra Space just proved him wrong. While Dragon capsules splash into the ocean like it's still the 1960s, Dream Chaser glides onto runways with revolutionary heat shields that survive 15 missions instead of just one. The impossible problem that even SpaceX couldn't solve. A small company from Louisville cracked the code. How they accomplish what the world's richest man couldn't. Let's dive right in. NASA's original choice of a winged spaceplane wasn't random. It was driven by the agency's engineers trained in aeronautics who saw space travel as a natural extension of flight. They didn't want capsules. They wanted spacecraft that could glide home to a runway. But there was another factor at play: politics. Budget constraints pushed NASA towards solid rocket boosters instead of more advanced liquid engines. Cheaper to develop. Yes, the best technical choice? Not even close. For 30 years, the space shuttle flew, until disaster struck. Twice. The Challenger in 1986. Columbia in 2003. Both catastrophes exposed a harsh reality. Those magnificent delta wings and thousands of fragile heat shield tiles made the system heavier, more complex, and dangerously vulnerable. So what did NASA do? They abandoned their dream and went back to basics. The capsule. Boeing and SpaceX both chose capsule designs for their NASA contracts. The reasoning? Simplicity equals safety. Fewer moving parts. Lower costs. Reliable atmospheric entry. Even Elon Musk, the man who lands rockets on drone ships, stuck with the traditional capsule. He was convinced it was the only viable option. But wait, isn't this the same Elon who embraces failure and innovation? The man famous for saying, "If things aren't failing, you're not innovating enough." Why the sudden conservatism with Dragon? Here's why: the heat shield problem. Reusable heat shields must survive temperatures reaching 3,000 degrees Fahrenheit, hot enough to melt most metals. They must withstand this inferno not once, but dozens of times without failing. A single failure means catastrophe. Even Musk admitted this was spaceflight's biggest engineering challenge. SpaceX's solution? Don't solve it. Just use ablative shields that partially burn away during re-entry, requiring extensive refurbishment after each mission. Dragon capsules parachute into the ocean like it's still the Apollo era, requiring naval recovery operations and extensive refurbishment. Is that really the future of space travel? While everyone focused on SpaceX's flashy rocket landings, Sierra Space was quietly revolutionizing the other half of the equation, the spacecraft itself. NASA initially rejected Sierra's Dream Chaser for crewed missions. Too complex, they said. Not ready for astronauts. But in 2016, something changed. NASA gave Dream Chaser another chance as a cargo hauler. The first vehicle, named Tenacity, is now preparing to prove the critics wrong. What makes Dream Chaser so special? Unlike the massive space shuttle, which required its own custom launch system with 7.8 million pounds of thrust, Dream Chaser is adaptable. It can ride atop various rockets, tucking its wings inside the payload fairing during launch. This flexibility isn't just convenient, it's a game changer. More launch options. Built-in contingency plans. No single point of failure. The space shuttle was a behemoth, 122 feet long with a payload bay stretching over 60 feet. It could deliver 60,600 pounds to orbit. Dream Chaser. Just 30 feet long, a quarter of the shuttle's size. Combined with Sierra Space's Shooting Star transfer vehicle, it can deliver 12,100 pounds of cargo to the International Space Station. Smaller means easier to handle. More sustainable operations. And critically, gentler re-entry experience with only 1.5 G-forces compared to capsules that can hit 3-4 G. That means sensitive scientific samples and delicate equipment arrive home intact, not battered by ocean impact like Dragon. But the real revolution is happening where you can't see it in the heat shield. The very problem Musk couldn't solve. Remember those space shuttle tiles? All 24,000 of them. Each one custom-made, with complex curves and intricate interfaces? NASA's engineers spent thousands of hours inspecting and replacing them between flights. Dream Chaser uses just 2,000 tiles. Each one is larger, 10 by 10 inches versus the shuttle's 6 by 6 inches. Fewer tiles mean fewer failure points. The The tiles themselves are stronger and lighter than those from the shuttle era. But Sierra Space didn't stop there. They partnered with Oak Ridge National Laboratory to create something truly revolutionary, a next-generation thermal protection system using silicon carbide-based materials. These new tiles are as strong as carbon fiber, but with the thermal stability of ceramics. They can withstand temperatures above 3,100 degrees Fahrenheit at speeds beyond Mach 17, roughly 13,000 miles per hour. Here's the breakthrough. While the outside faces searing heat, the inner layer keeps the spacecraft safe and cool. And instead of surviving just 5 missions like the shuttle's tiles, these can handle at least 15 before needing replacement. That's not just an incremental improvement. It's exponential. It's what Musk called impossible. Space economics comes down to reusability. SpaceX proved this with first-stage boosters. But the spacecraft itself? That's been the missing piece. When Dragon splashes down, it requires naval recovery operations with ships and helicopters, extensive refurbishment of the heat shield, saltwater contamination cleanup, complete disassembly and inspection. Dream Chaser. It glides onto a runway like an airplane. No ocean, no salt water, no parachutes to repack. Just roll it into a hangar, refuel, and it's ready to go again. This breakthrough solved the exact challenge Musk called the biggest engineering problem in spaceflight. It's not just about withstanding heat, it's about materials, structure, and long-term reliability. Sierra Space has created what Musk couldn't: heat shields that won't crack, warp, or degrade even after multiple missions. They can handle extreme thermal cycling without suffering fatigue or structural failure. Dragon's approach? Looking more obsolete by the day. If your shield is reusable but requires thousands of hours of inspections and replacements after every flight, what have you really gained? The Space Shuttle's maintenance nightmare proved this point. Each of those 24,000 tiles needed constant attention. The result? Turnaround times of months instead of days, and costs that spiraled to over $1.5 billion per launch. Sierra Space is targeting both safety and affordability by reducing tile count, streamlining inspections, and eliminating ocean recovery operations. And there's the integration factor. A heat shield can't be an afterthought. It must fit seamlessly into the spacecraft's aerodynamic design, structural layout, and mass distribution. This is especially critical for future missions beyond Earth orbit. As companies race toward rapid reuse and deep space exploration, the perfect balance of durability, reusability, and efficiency becomes essential. And Sierra Space just leapfrogged everyone else in the race. Sierra Space isn't just competing with SpaceX and Boeing, they're rewriting the rules of the game. While billions are poured into R&D and testing, not every attempt will succeed. That's the nature of innovation. But breakthroughs like Dream Chaser's heat shield bring us closer to routine space travel. Will SpaceX adapt? Will Musk admit he was wrong about capsules being the only viable design? Or will Sierra Space leapfrog the competition entirely? The question now isn't just who will win this space race, it's whether we're witnessing the birth of a completely new paradigm in space transportation. After decades of splashdowns and parachutes, are we finally returning to the dream of spacecraft that fly like aircraft, but with revolutionary technology that makes it practical and economical? And if Sierra Space has solved what Musk called impossible, what other impossible space challenges might soon fall? Sierra Space didn't just improve an existing design, they challenged the very foundation of modern spacecraft philosophy. They proved that sometimes the best way forward requires looking back with fresh eyes. What seemed impossible to Elon Musk was simply an engineering challenge waiting for the right team with the right approach. Dream Chaser isn't just competing with Dragon, it's reimagining what reusable spacecraft can be. The implications go far beyond NASA contracts. This breakthrough could transform space tourism, satellite deployment, and even future missions to the Moon and Mars. If you're as fascinated by these space innovations as we are at Space Corps, hit that subscribe button and turn on notifications. Our mission is bringing you the cutting edge of space technology every week, breaking down complex topics into stories that inspire. Drop a comment below. What impossible space challenge should we explore next? Until next time, this is Space Corps, where the impossible becomes reality, one breakthrough at a time.
Raptor 2 engines are being scrapped this year, and Elon Musk finally reveals why. The explosion at SpaceX's Ship 35 static fire test wasn't just an anomaly, it exposed fundamental flaws in the engine's design that SpaceX can no longer ignore. While Musk initially promised Raptor 2 would revolutionize space travel, 3 failed launches and a catastrophic vacuum engine explosion tell a different story. What went so catastrophically wrong? The shocking truth. Raptor 3 was already being quietly developed as the emergency fix, with 21% more thrust, better cooling systems, and zero bolted joints. Is this SpaceX's most critical engineering pivot yet? Let's dive right in. When Elon Musk unveiled Raptor 2 in February 2022, it wasn't just another engine. It was supposed to be SpaceX's golden ticket to Mars. Standing proudly on stage, Musk presented what seemed like an engineering marvel: sleeker design, simplified manufacturing, and most importantly, raw power that dwarfed its predecessor. On paper, Raptor 2 was perfect. In reality, it became SpaceX's most challenging puzzle yet. "This engine will revolutionize access to space," Musk declared back then. But fast forward to 2025, and that revolution has been more about learning harsh lessons than celebrating victories. What exactly went wrong with the engine that was supposed to change everything? Let's break down the evidence. During Starship's first flight, 3 Raptor engines failed to ignite before liftoff. Think about that. The most advanced rocket engine on Earth couldn't even start properly. Starship lifted off with just 30 of 33 engines running. Then 27 seconds into flight, something SpaceX engineers cryptically called an energetic event knocked out several more engines. But what does energetic event actually mean? In aerospace engineering terms, it's code for something exploded that wasn't supposed to. This cascade failure left mankind's most powerful rocket spinning uncontrollably through the atmosphere. Flight 2 seemed promising at first. All 33 engines fired perfectly at liftoff. But the success was short-lived. At 2 minutes and 55 seconds after stage separation, when Super Heavy attempted to flip around for its boost backburn, multiple Raptor engines refused to reignite. The result? Another flight termination. Wait, notice the pattern forming? The Raptors work fine at initial ignition, but fail during reignition attempts in flight. Why would this happen? The answer lies in a critical design change that most space enthusiasts completely missed. Raptor 1 used a reliable torch igniter inside the main combustion chamber, essentially a small rocket that lights the big rocket. But Raptor 2? SpaceX completely abandoned this proven approach. To this day, Musk hasn't revealed exactly what ignition system replaced it. Imagine removing the spark plugs from your car and replacing them with something else, something unproven. That's essentially what happened with Raptor 2. What makes this particularly dangerous is the full flow stage combustion cycle that Raptor uses. Unlike conventional rocket engines, Raptor needs successful ignition at 3 critical points simultaneously: the fuel side preburner, the oxidizer side preburner, and the main combustion chamber. If any one of these fails to ignite properly, you're not dealing with a simple misfire, you're facing a potential bomb. Liquid oxygen and methane don't just sit there when they mix without igniting. They create one of the most volatile combinations imaginable. After Flight 7's failure, SpaceX promised an upgraded ignition system. But then came Flight 8, where not 1 but 2 engines failed during boostback reignition. The fix clearly wasn't fixing anything. But that's just the beginning of Raptor 2's troubles. During recent flights, Starship's upper stage engines encountered something engineers fear more than almost anything else: unexpected harmonic resonance. Think of it like this. Imagine a wine glass shattering when a singer hits just the right note. That's harmonic resonance. Vibrations that match an object's natural frequency, amplifying until something breaks. In Starship's case, these vibrations were attacking the most vulnerable parts of the Raptor engines: their powerhead components and propellant feed lines. The result? Critical methane leaks that ignited inside the engine bay, essentially starting fires in one of the worst possible places on a rocket. What's truly concerning is that these resonance issues never appeared during ground testing. They only emerged in actual flight conditions. This suggests that something fundamental changed between Starship's testing environment and its flight configuration. The most likely culprit, structural modifications in the new Starship Block 2 design, particularly in how the propellant plumbing is arranged. And then came the most alarming incident yet. Just last week, during what should have been a routine static fire test with Ship 35, disaster struck. One of the Raptor 2 vacuum engines